In this video we will be looking at Euclidean geometry. But first, just a short introduction on how to do mathematics. Number and copy the examples and ask your tutor or teacher if there are anything that you do not understand. Then number the questions. Unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answers. Mark your work. If the answers are incorrect, write down the corrections and make sure that you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. Now, an overview of this video, we will start by going through all the theorems, and then we will look at simple sums where we're going to apply each theorem, and then finally we'll look at practice questions, the kind of questions that you can expect in your final exam. Now for theorem 1, if I have a circle with center O and I have a chord drawn BC, and then I draw a line from the center of the circle to the chord, and that is perpendicular to the chord, then that tells me that that line will bisect my chord if it is perpendicular. So BA will then be equal to AC. So the official theorem states that a line drawn from the center of a circle perpendicular to a chord bisects the chord. And then the statement that you use as your reason, if you use this theorem, line from center is perpendicular to chord. Now the converse of theorem 1, if I have a circle once again with center O, and I draw my chord BC, and then I draw a line from the center of the circle that bisects the chord, then we can state that if it bisects the chord, then those two lines are perpendicular to each other. So the official statement says that a line drawn from the center of a circle to the midpoint of a chord will be perpendicular to the chord. And then the reason that you state is line from center to midpoint of chord. Now for theorem 2, I draw a circle, and then in that circle I draw a chord, and also I draw a line that bisects my chord perpendicular, meaning that it cuts it in half at an angle of 90 degrees. So if it does that, then I can say that the line that I've drawn will go through the center of the circle. So theorem 2 states the perpendicular bisector of a chord passes through the center of the circle, and the official statement is perpendicular bisector of chord. Theorem 3, I have a circle with center O, and then from BC, the arc BC, I subtend my angle to the center of the circle, and then from those same 2 points I subtend an angle to the circumference of the circle, and then we can state that the angle at the center of the circle will be twice the size of the angle at the circumference of the circle. So theorem 3 says that the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at any point on the circumference of the circle. Then the angle at center is equal to 2 times the angle at the circumference. Now for corollaries, in that case, it means that if I have my arc at 180 degrees, that means it's the diameter of the circle, then it will subtend an angle that is half of 180, which is 90. So theorem 3 says that the diameter subtends a right angle at the circumference of the circle, or alternatively, if the angle at the circumference of a circle is a right angle, then we can say that it is subtended by the diameter. And if you use this theorem, you state angle in semicircle. Then for theorem 4, I have a circle, and then from an arc CD, I subtend my angle to the circumference of the circle, and then from those same 2 points, I also subtend it to another point on the circumference of the circle, and then those two angles will be equal. So the theorem says the angles on a circle subtended by a chord of the circle on the same side of the chord are equal. And we can simply state that as angles in the same segment as our reason. Then for the corollaries, so if I have my chord CD and on another place in the circle I draw the same chord but of equal length, then the angle subtended by that chord will also be equal to the angle of the other chord as long as they are in equal lengths. So theorem 4 says equal chords subtend equal angles at the circumference of a circle. Equal chords subtend equal angles. Then the converse of theorem 4 is if I have a quadrilateral, or if I subtend two angles from CD and those two angles are equal, then if they are equal, then we can assume that ABCD is a quadrilateral. So if two angles subtended by the same line are equal, then ABCD is a cyclic quadrilateral. Angles in the same segment. Then for theorem 5, so once again I have a circle, and then inside the circle I draw a quadrilateral, and then if you have a cyclic quadrilateral, then it means the opposite angles are supplementary. So that means that angle C plus angle B will equal 180, and also that angle A plus angle D will equal to 180. So the theorem says that the opposite angles of a cyclic quadrilateral are supplementary, and our reason will be opposite angles of a cyclic quad. So the corollaries, if I extend CD, then the angle, the exterior angle, will be equal to the interior opposite angle. So the theorem says the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. And our reason is exterior angle of a cyclic quadrilateral. Then the converse of theorem 5, if I have a quadrilateral ABCD and my two opposite angles are equal, either supplementary, either C plus B is equal to 180 or that A plus D is equal to 180, then I can state that it will be a cyclic quadrilateral. So a quadrilateral is a cyclic quadrilateral if the opposite angles are supplementary. So just simply opposite angles of quad supplementary. Then for theorem 6, I have a circle, and then outside the circle I have a point, and from that point I draw my two tangents where my points of contact are A and B. So these two tangents then, which is drawn from the outside of the circle, AC will then be equal to CB, because theorem 6 states that two tangents drawn to a circle from the same point outside the circle are equal in length. And then the reason tans from the same point. Then for theorem 7, I have a circle and I have a tangent to the circle, and then from that same point of contact I draw a chord. Then the angle between my tangent and my chord will then be equal to the angle subtended by that chord. And similarly, if I draw a chord from A to C, my angle between my tangent and chord will be equal to the angle subtended by AC. So the theorem, the official theorem, says that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle subtended by the chord in the alternate segment. And the reason is the tan chord theorem. And now a summary. So this is everything that you need to know off by heart when you go into the examination, so that you can use your theorem. So the first theorem, for theorem 1 to 2, we have that a line from the center to the is perpendicular to the chord. So that is when we see that the line from the center is perpendicular to the chord, and then we can say that it bisects it. And then also the converse of that, when we see that it bisects it, then we can know that they are perpendicular. And then if we need to know that the line goes through the center and we see that it perpendicularly bisects it, then we use that reason. So for theorem 3, we have that the angle at the center is 2 times the angle at the circumference. And also, if it's a diameter, it's angles in a semicircle. Then for theorem 4, we have angles in the same segment that are equal. And also equal chords subtends equal angles if we have to prove the quad a cyclic quad. And then for theorem 5, we have that opposite angles of a cyclic quad, they are supplementary. And then exterior angle of a cyclic quad is equal to the interior opposite angle. And then opposite angles of a quad are supplementary, and that is once again when you have to prove for a quad being a cyclic quad. And then theorem 6, here we have that the external point from a point, the two tangents drawn from a point, will be equal in lengths, and the reason tans from same point. And then theorem 7, we have the tan chord theorem, where the angle between a tangent and a chord is equal to the angle subtended by that chord. And that was all the theorems. So next we're going to look at how to apply the theorems. Now, in this question, it states that in the circle with center O, LO is 26 centimeters, OP is 10 centimeters, and OP is perpendicular to MN. So we need to calculate the length of MN. Now, if we look at our summary, the first thing we look at is which one of the theorems can we identify. And it seems that this theorem 1 and theorem 2, because we have this chord and the line from the center is perpendicular to it, so that means that these two are equal. MP is equal to MN. So we need to find this entire chord, but what else can we use? We can see that this LO is the radius, and the radius here is also this is also the radius of the circle. So this is then equal to 26 centimeters. And then over here, since this is a right angle, we can use the theorem of Pythagoras, and then we can calculate MP's value. And then if we have MP and we know that MP is equal to PN, then we can just multiply that by 2 to get MN's distance or length. So let's start by doing that. The first thing we're going to say is that we say that MO is equal to 26 centimeters, and our reason is radii. Then we want MP. So to find MP, we want to say that OM squared is equal to OP squared plus MP squared. And this is the reason is Pythagoras. And then finally we can substitute our values and solve for the unknown. So OM we have as 26 squared equals to OP, which is 10 squared plus MP. So if I solve for MP squared, I take the 10 over, so MP squared is equal to 26 squared minus 10 squared. So MP is then the square root of 26 squared minus 10 squared. And then if we put that on the calculator, we have the square root of 26 squared minus 10 squared. And this gives us 24. Alright, so now since MP is 24, now we can say that that MP is equal to PN. Our reason is line from the center perpendicular to the chord. So line from center perpendicular to chord. And then since MP is equal to PN, we know that both are 24. So therefore we have that MN is equal to 2 times MP, which is equal to 2 times 24, which is equal to 48. And that's in centimeters. Now for this question, in a circle with center O, the radius is 10 centimeters and the chord PR is 8. So PR from here to here is 8. And then calculate OQ correct to 1 decimal place. So we need OQ. Now since this is the radius, we can also know that OP, which is also the radius, will also be 10 units or 10 centimeters. And then we know that, see this line from the center of the circle cuts this chord at 90 degrees. So that means that the PQ and QR will, or PR will be bisected by that chord. And then since we know that this is half, we can see that this then will be 4. And if we know this is 4, we can use Pythagoras to find OQ. Alright, so now to get started, we can say that PO or OP is equal to 10 centimeters, and that's the radii. And then we can say that PR is 8, and that's a given. But we know that PQ is equal to QR, and our reason is line from center is perpendicular to chord, and therefore we know that PQ is half of PR, so that would be half of 8, which gives us 4. And then we know that according to Pythagoras, this is the short side, so we say OQ squared, or QO squared, is equal to the long side, which is OP squared minus the other short side, which is PQ squared. So PQ squared. And then if I substitute in my values, I have 10 squared minus 4 squared. So this gives me 100 minus 60 minus 16. And then if I take the square root of that, so OQ is the square root of this, and if we type that in, we've got the square root of 100 minus 16. And this gives us 2 square roots of 21 centimeters. Okay, then for the next one, in this one, we're just going to see which one are we going to use. So we have here, if we can recognize, we see this is actually theorem 3 that we recognize here, because we know that the angle that's subtended at the center is twice the angle subtended to the circumference. So this then will be just double that. Now if we put that over here, we'll say that O, or A, angle A in this case, so A is then equal to 2 times by 32 degrees, and the reason then is angle at center will be equal to 2 times angle at the circumference. Right, and then therefore A is equal to 64 degrees. Right, and then for the next question, so we have C here as the angle subtended at the center. So C is 2 times 48 degrees, and once again our reason will be that angle at center is equal to 2 times the angle at the circumference. So therefore C then is equal to 190 or to 96 degrees. Now for the following, we need to find D's value. And if we look at what we have to work with, can we recognize any of these? We see that we have the diameter, and then we have an angle subtended by the diameter. So this means that this must be 90 degrees. And therefore, we know that we've got this triangle, and we know that angles of a triangle add up to 180. So therefore, that's how we can find D by adding up the angles, subtracting or equal to 180. So the first thing we're going to say is we're going to say that this angle is equal to 90. So we can say that A plus 90 degrees plus 40 is equal to 180 degrees. And our first reason would be angles of a triangle, and also that we have subtended diameter subtends, or angle in semicircle. And then solving for A or for D, we have D is equal to 180 degrees minus 90 degrees minus 40. So this gives me 90 minus 40, so this is then, D is then 50 degrees. Now for this question, we have that, or if we look at, can we recognize anything, then this looks like theorem 4, where we have two angles that's subtended from these points, and the one is 42 degrees and the other one is B, and then also from the other side we have this angle that's being subtended, and this one subtended. So this angle will then also equal to this angle 31, and also this will equal to this, which is 42. Now to write that down, we can say that B is equal to, or if we start with A is equal to 31 degrees, and our reason is angles in same segment, so angles in same segment. And then B is equal to 42 degrees, also angles in same segment. Now for this question, we need to find C and D. Now C is also subtended like 40, this angle over here. We've got this one over here subtended, and that means that these two angles are equal, as we can see here from theorem 4. Then we have that C is equal to 24 degrees, and our reason angles in same segment. And then we need to find D. Now we can see that these two lines are parallel. That means that these two angles over here are alternate angles. So our D is also equal to 24 degrees, and that is alternate angles. In the following one, if we look at our summary, this one we can recognize as theorem 5. We know that opposite angles of a cyclic quad add up to 180 or supplementary. So for A, I'm going to say that A plus 72 degrees should equal to 180. And our reason, therefore, is opposite angles of a cyclic quad. So opposite angles of cyclic quad. And then A is equal to 180 minus 72, and this will then equal to 108 degrees. And then B, the same story, B plus, because these guys are opposite, so B plus 130 degrees is equal to 180, and therefore B, and the reason will also be opposite angles of cyclic quad, and then B is equal to 180 degrees minus 130 degrees, so this is equal to 50 degrees. And now if we look at this one, this is also theorem 5, actually much easier because this is the exterior angle of a cyclic quad, which is equal to the interior opposite angle, and therefore we can simply say that E is equal to 110 degrees, and our reason is exterior angle of cyclic quad. Now in this question we need to find K, L and M. The first thing we can see is that K is equal to this exterior angle. If we look at our theorem over here, and then what we can do is, since these two lines are parallel, we have co-interior angles here. So this K plus L is equal to 180, or they are supplementary. And then we also know that actually easier, we can use one of two methods to find M, because these two opposite angles are supplementary, or we can just use these alternate angles, which is actually a bit easier, so we'll use that. Now to get started, we know that K is equal to 55 degrees, and our reason for that is exterior angle of cyclic quad. Then we need to find L, so we know that K plus L is equal to 180, and that's co-interior angles. So solving for K, or solving for L, we just substitute in K's value, which is 55 degrees, plus L is equal to 180 degrees, and then L is equal to 180 degrees minus 55 degrees. So this then gives me 125 degrees. And then finally, to find M, I'm just going to say that M is equal to 55 degrees, and the reason is alternate angles. Now for this question, we need to find P and Q. Alright, so let's just look at if we can recognize the theorem. This looks like theorem 6 though, so if we can use this, we know that this side must be then equal to this side. And if we know that this side is equal to this side, this makes an isosceles triangle, which means that this angle of 62 is equal to this angle of 62. And if I know this angle, I can use angles of a triangle to find P. So that's my first approach to find P. And then we need to find Q. So what else can we see? Here we see a triangle in a circle. Then we always look out for Tankour theorem. And we see that this is the angle between the tangent and the chord, and this is the angle subtended by the chord. So that means that this Q is also 62 degrees using the tan chord theorem. So now to get started, we have that we need to state that these two lines are equal, but then we can say here that this angle is 62. So we have that we have isosceles triangle. So P is then equal to 180 minus 62 degrees minus 62 degrees, and this is, if we walk through everything, we have that isosceles we have isosceles triangle, and then we have angles of triangle, and then P will be equal to 180 minus, so if we have 180 minus 62 minus 62 equals to 56. All right, so this is just to actually give you insight in calculating the actual values or seeing the theorems in, but the actual way of writing this out, we'd have to state that first we'd have to state, but there's no names for the angles in these types of questions. So we'll have to state that these are equal if we have the names, and then we'll have to state that this angle is 62 with the reason it's isosceles, and then we'll have to state angles of a triangle. All right, and then finally we can say that Q is equal to 62 degrees, and that is the tan chord theorem. Okay, and then we need to find L. So once again, if we look at this, we can see this theorem 6 over here. And to find L, what we're going to do is we know that since these two are tangents from the same point outside of the circle, we know that this is equal to this, and therefore this is also 15. And now also we know that the radius at the same point of the tangent, they are 90 degrees to each other. If you have a radius of the circle to the circumference and the tangent that goes through that point, these two lines will be perpendicular to each other. So in that case, we can use Pythagoras. So therefore, L squared will be equal to 8 squared plus 15 squared. And we're using Pythagoras, and then we can just solve for L. That's being the square root of 8 squared plus 15 squared, which is equal to 17. Then for question, the next question, now we need to find A, B, and C. And if we look at our theorems, we can see that this is the tan chord theorem that we're going to use. So first of all, we know that this angle is equal to A, and we also know that this angle is equal to B, both of these tan chord theorem. And then finally, to find C, we can use either one of angles on a straight line, which add up to 180, or we can use angles of a triangle, which also adds up to 180. So first thing, A is equal to 72 degrees, and our reason is tan chord theorem. And then we know that B is equal to 40 degrees, also tan chord theorem. And finally, C plus A plus B will be equal to 180 degrees, and let's just use angles on a straight line. And then substituting our value, C plus A's value is 72 degrees plus 40 is equal to 180. So C is equal to 180 minus 72 minus 40, and that's equal to 180 minus 72 minus 40. So this gives us 68 degrees. Right, and then for this question, we need to find E and D. Now, once again, looking at the summary, we see this is the diameter, and it is subtended. This angle is subtended by the diameter, so this is like theorem 3 that we're applying there. And then we look at D, and we see that this angle will be equal to this angle, and that's just simply the tan chord theorem. So this is quite simple. We know that E is equal to 90 degrees, and our reason is angle in semicircle. Right, and then D is equal to 30 degrees, and that's simply the tan chord theorem. Right. Now for this question, and once again, if we look at the summary, this is the Untitled theorem that we're going to apply again. So once again, this angle between this chord and this tangent will be equal to the angle subtended by that chord. So that's going to be 36 degrees. Then to find h, we can use either one of Untitled theorem again, because this angle is also subtended by this one, or we can use angles in same segment. So let's just do that. So this will also be then 36 degrees. Now finally, to find this angle, we know that this is the radius, and we can see that it subtends a 90-degree angle, and then we can use angles of a triangle to solve for I. So first of all, we're going to say that G is equal to 36 degrees, Untitled theorem. And then H, which is equal to G, which is equal to 36, we can say angles in same segment. And then finally, we know that I is equal to, or I plus 90 degrees plus H is equal to 180. So that's angles of a triangle. And to solve for that, I is equal to 180 degrees minus 90 minus 36 degrees. So this will then give us 180 minus 90 minus 36, 54 degrees. And that was just a few very small and simple examples on applying theorems. So next we move on to the more complex questions that you can expect in the exam. Okay, so for question 1, in the diagram below, PT is a diameter of the circle with center O. M and S are points on the circle on either side of PT. And then MP, MT, MS and OS are drawn. So M2 is 37 degrees. Calculate with reason the size of angle M1. So for angle M1, it's over here. Now, if we look at our theorems, we have the following theorem. So what can we recognize? We know that this is the diameter. So immediately if you see a diameter, think of the angle subtended, and this one is then 90 degrees. So that means if we want to find M1, we'd simply say 90 minus 37 degrees. And then if we want to find O1, if we look at O1 here, this is subtended to the center of the circle, where this one is subtended to the circumference. So this would then be 2 times M1's value. Right, so now let's do that. So for 1.1, we have that PMT is equal to 90 degrees because it is its angle subtended, or its angle in semicircle. Right, and then we can say that therefore angle M1 plus angle M2 will equal 90 degrees, and then I substitute in M2's value. So M1 plus 37 degrees equals to 90 degrees. So M1 is equal to 90 minus 37. And then that would equal, so if we just do that, 90 minus 37. So that gives me 53 degrees. And then for 1.2, so O1 is then equal to angle O1 is equal to 2 times angle M1. And the reason is that we have angle at center is equal to 2 times angle at circumference. And therefore O1 is equal to 2 times 53 degrees, and that gives us 106 degrees. So question 2, in the figure below, AB and CD are chords of the circle with center O, and then OE is perpendicular to AB. CF is equal to FD, so CF equal to FD, OE is equal to 4, so OE is equal to 4, and OF is equal to 3, and then CD is equal to 8, so all of this is equal to 8. Okay, so calculate the length of OD, so we want to get this length. Alright, now the first thing we need to do, we can see that this looks like a right angle triangle, and we can say that OFD is equal to 90 degrees and state our reason, because OFD is equal to 90 degrees. So our reason is that a line from center, or line from the center to the midpoint of the chord. So line from center to midpoint of chord. Right, then since this is 90 degrees, we can use Pythagoras. Now before we do that, we know that DF is equal to FC, because that's given, and then therefore FD is half of CD, so FD will equal half of CD, and that's then equal to 4. And then we can use Pythagoras, so OD squared is equal to 3 squared, or OF squared, plus FD squared, and the reason is Pythagoras. So if we substitute in our values, we've got OD is equal to the square root of 3 squared plus 4 squared. And that's equal to 9 plus 16, which is 25, so this is then equal to 5. Then for 2.2, this was 2.1, 2.2, hence calculate the length of AB. So AB over here, and the first thing we need to always keep in mind is that the radius of the circle is equal everywhere. So if we know this is 5, then my radius over here will also be 5. Right, and then we can see that this line from the center of the circle to this chord is perpendicular, therefore these two are equal. Now before we state that, we can just work out BE using Pythagoras first. So BE squared is equal to the long side squared minus the short side. So that's OB squared minus OE squared. And that's Pythagoras. And substituting in our values, we have BE is equal to the square root of OB, the long one is 5 squared, minus 4 squared. And that's equal to, if we put that in, square root of 25 minus 16. And that gives us 3. Right, so if this is then 3, we know that BE is equal to BA, and our reason is angle or line from center, perpendicular to chord. Okay, so if that's equal, then that means that this BA will be twice BE. So BA is equal to 2BE, and that's equal to 6. Now for question 3. In the diagram, M is the center of the circle passing through the points L, N, and P. M is produced, or PM is produced. PM is produced to K, and then KLMN is a cyclic quadrilateral in the larger circle having KL equals to MN. LP is joint, so KML is 20. So this is 20. Now write down with a reason the size of NKM. So NKM. Now first of all, let's just look at our reasons here, or our theorems. We have this angle. If we look closely, we've got this one is given that it's equal to this one. And I can see that this 20 is subtended by this chord, and then the one they are referring to, K1, is subtended by an equal chord. So that means that this one will also be 20 because they are subtended by equal chords. And then for number 2, give a reason why KN is parallel to LM. So KN is parallel to LM. So as we can see, this is then, if this is also 20, then these two guys are alternate angles. The alternate angles are equal, so therefore these are parallel. So let's look at writing that. So we've got 1, and then the size of NKM, so NKM is equal to 20 degrees. So our reason is angles subtended from the same or equal chords subtend equal angles. So equal chords subtend equal angles. Then for 2, give a reason why KN is parallel to LM. So therefore it is because the alternate angles are equal. So alternate angles are equal. And then for 3, prove that KL is equal to LM. So KL is equal to LM. All right. Now, if I look at this smaller circle, then this is actually the radius, and this one is also then the radius. Now, therefore, we have that LM is equal to NM, and that's the radii. And then we know that NM is equal to KL, or KL is also equal to NM, and therefore NM is equal to, or therefore LM is equal to KL. So number 4, calculate with reason the size of KNM. So KNM, and what we can do here, so we're going to say that since this chord is now equal to this one, we know that it also subtends an angle of 20 degrees. So this angle then will be 40. Now if we look at this cyclic quadrilateral, we know the opposite angles of cyclic quad add up to 180. So then we can find this angle, which is supplementary to that one. And then we know that these two angles, or this one plus this one, will be co-interior. So the first thing I'm going to say is then, so this would then be, if we say that LKM, so LKM will be equal to 20, where equal chords subtend equal angles. And then we can say that NKL is 40. So this LMN, so LMN plus NKL is equal to 180 degrees, so that's opposite angles of cyclic quad. And then we substitute in our value for NKL. This gives us LMN plus 40 degrees equals to 180 degrees. So LMN is equal to 140 degrees. And then finally we can say KNM, so KNM plus KML is equal to 180 degrees. This is co-interior angles. And we know that KN is perpendicular to LM. And therefore KNM is equal to 180 degrees minus the 140 degrees, which is then equal to 40 degrees. So this was 4.1. Then finally 4.2, LPN. So LPN. So once again, in the smaller circle, we can see that this angle LMN subtends at the center of the circle and then also to the circumference. So that means that LPN is half of LMN. And our reason is that the angle at center is 2 times angle at circumference. So this is then half of 140, which then gives us 70 degrees. So for question 4, in the figure below, DCO is 25 and O is the center of the circle. A, B, E, C, and D are points on the circumference. Calculate, giving reasons, the sizes of. So we start with D1. Now D1, if we look at this triangle, we see this is the center. So from OD, that's our radius, and OC is also our radius. So then it means that we're working with our isosceles triangle where these two base angles are equal. So for 1, angle D1 is equal to angle DCE, or no, not DCE, or angle C over here, or equal to 25 degrees. And our reason is equal sides equal angles. Then for 2, so O1, now this isn't so obvious to see, but this O1 is subtended to the center of the circle, and then it's also subtended to D. So therefore, O1, angle O1, is equal to 2 times angle D1. And our reason is angle at center is equal to 2 times angle at the circumference. So it's going to be 2 times 25, so this is going to be equal to 50. Then for 3, so A1 over here, we see these two angles are subtended from the same chord, so therefore if this is 25, then this would also be 25. So A1 is equal to 25, and our reason is that angles in the same segment and then for number 4, we need to find E. So we know that this is a cyclic quad, and therefore opposite angles of cyclic quad are supplementary. So we know that angle E plus D1 is equal to 180 degrees. So the reason opposite angles of a cyclic quad. And then D1 being 25, so E is equal to 180 degrees minus 25 degrees, and that gives us 155. And for question 5, A, B, C, and D are points on the circumference of the circle in the diameter below. EFC is a tangent at C, and B1 is equal to B2. So these two angles are equal. Now for number 1, if B1 is x, find with reason 2 other angles equal to x. So this is x, and because it's given that it's equal, this obviously is also x. So if I look at my theorems, which one of these do I recognize? I can see this bow tie over here, so that means that angles subtended from the same segment, angles in the same segment, means that C2 is also x. And then whenever I see a tangent, I always look out for the tangle theorem. So if I have a triangle over here, then this angle is also equal to this angle between the tangent and the chord. So this would also then be x. So if we write those reasons down, we've got that C2, angle C2 is equal to B1, which is equal to x, and our reason is angles in same segment. And then for the second angle, we know that C1 is equal to angle C1 is equal to angle B2, which is equal to x. And the reason is simply the tan chord theorem. Then for 2, so hence show that DC bisects AFC. So we need to show that DC bisects ACF. And this is quite easy because it's already proven that, or we already showed that these two angles are equal. So we know that C1 is equal to C2, and then we therefore DC bisects ACF.